Welcome back to another episode on circuit analysis. Today we are diving deep into the work of electronic components and we'll be treating capacitors and inductors as energy storage elements. This video will unravel the mysteries of these essential components and show you how they power the devices we use every day. In this video, we'll introduce two new passive circuit elements, the capacitor and the inductor, each of which has the ability to both store and deliver finite amounts of energy. They differ from ideal sources in this respect since they cannot sustain a finite average power flow over an infinite time interval. Although they are classed as linear elements, the current voltage relationships for these new elements are time dependent, leading to many interesting circuits. The range of capacitance and inductance values we might encounter can be huge, so at times they may dominate circuit behavior, and at other times were essentially insignificant. Such issues continue to be relevant in modern circuit applications, particularly as computer and communication systems move to increasingly higher operating frequencies and component densities. So we already know the difference between active and passive elements. Active element is an element that is capable of furnishing an average power greater than 0 to some external device, while a passive element is defined as an element that cannot supply an average power that is greater than 0 over an infinite time interval. And of course, example of active elements are sources, the voltage source, the current source. The operational amplifier is also an active device, but passive elements are capacitors, inductors, resistors, and some other components. So here we want to talk about the capacitors first before treating the inductors. The voltage current relationship for the capacitor is what? I is equals to C dV dt. I will advise you to memorize this formula as this is a proved and experimented formula that the relationship between current and voltage in a capacitor is I is equals to C dV dt. So where V and I satisfy the conventions for a passive element, we should bear in mind that V and I are functions of time. If needed, we can emphasize this fact by writing I of t and V of t. Right? We can write I of t is equals to C d dt V of t. So just to show that I and V are functions of time. And of course, C is in farad, that is the unit of capacitance is farad, which is also known as 1 coulomb per volt. And of course, you know the unit of current and unit of voltage, which is straightforward. So the symbol for a capacitor is this. Alright, so the voltage on the capacitor will call it V, and the current going through the capacitor will call it I. And of course, let's say it's in terms of t, right? I of t and V of t. And of course, the value of the capacitor is the capacitance. So capacitors, they are constructed with two parallel conducting plates of a particular area separated by a distance d and has a capacitance C. And of course, if you want to get the capacitance of a capacitor in terms of internal properties, we will say the capacitance of a capacitor is equals to epsilon A over D. E is a Greek alphabet called epsilon, and epsilon is a property of the dielectric of a capacitor, which is called the permittivity of free space. The permittivity, not only free space have permittivity, every material has its own permittivity, right? So but for a free space, that is, if the dielectric is just a free space, the permittivity is usually 8.85 times 10 raised to power minus 12. So that's the permittivity. And of course, if you know the area of the area of the two parallel plates, and the distance in between the two plates, we can get the capacitance of the capacitor. So that is very, very simple. So let's get a more expressed relationship between the voltage and the current through a capacitor. We said that I of t is equals to C dV dt, right? which means that I can cross multiply, which means that I can have c dv, right, is equals to I of t dt. So if I divide both sides by c, I will have dv is equals to 1 over c I of t dt. So what does that mean? So if we integrate between times t naught and t, right, so what do we have? We have t naught, that is t at the beginning of our sampling, and of course we integrate I too from t naught to t. So what do we have? When we integrate the v, we have v, right, and we put our boundaries t naught t, right. Don't forget it is v of t, that's and 1 over c. When we integrate I with respect to t, we have it, right. But in this case, let's just still leave it like that. We still have integral t naught t I of t dt. So if we insert t and t naught, we have v of t minus v of t naught is equals to 1 over c integral t naught to t I of t dt. And of course, this v of t naught depends on what the voltage is at the beginning of the sampling, right? So if we integrate this, we can remove this boundary and just add a constant of integration, right? So what does that mean? Basically, this minus v naught of t is a constant of integration, so we can replace it with k, or we can still leave it as v of t naught. So basically, we know that v of t will be equals to 1 over c integral from t naught to t I of t dt. Then if we bring this to the other side, it will be plus k. This is a more composed form of the relationship between voltage and I through a capacitor. And of course, we can also define capacitance, that is the relationship between capacitance and voltage, as Q is equals to CV, right? Q is amount of charge. Q is equals to the amount of charge, which the unit is coulombs. Amount of charge in coulombs. Then of course C is capacitance, and V is voltage. So let's take an example. So this is the example we'll be using to explain capacitors and the relationship between current and voltage in a capacitor. So find the capacitor voltage that is associated with the current shown graphically above. The value of the capacitance is 5 microfarad. So you can see that the current time graph shows that any time before t is equals to 0, the current is 0. When the time is in between 0 and 2 milliseconds, the current is 20 milliamperes. But any current that is greater than 2 milliseconds, the current is 0. Then for the voltage graph too, when the time is less than 0, the voltage is 0. Between 0 and 2, it has a value, right? It has a value. But when t is greater than 2, it is constant. That is V is equals to 8. So we are going to take this segment by segment. So first segment is when t is less than 0. Remember our formula. The formula is V of t is equals to what? The integral 1 over c t naught to t I of t dt plus V of t naught. Right? So in that case, for us to get the voltage at 0, what does that mean? It means that V of t that's what we are looking for. V of t naught will be the where it started. So because it tends to infinity, we don't know where it started, so we just say v of minus infinity. Sorry, this is the current graph. So we are looking at I of t will be equals to 0 in that case. And when v is less than 0, v of t of infinity is what? V of infinity minus infinity, because from the left, is 0. Because anything less than 0 for voltage is 0. So if you are to put this inside the equation, we have what? V of t is equals to what? This is 1 over c integral of 0, right? And integral of 0 is still 0, plus v of t naught is v of minus infinity, right? So what do we have? We have 0 plus 0. Therefore v of t is equals to 0 for t less than or equals to 0. So this is our first case. That is when t is less than or equals to 0. So the second case is when 0 is less than t less than or equals to 2. That is t naught is equals to 0 and t equals to 2. So what do we do? V of t is equals to what? 1 over c integral from t naught to t I of t dt plus v of t naught. So what do we have? 1 over 5 times 10 raised to the power minus 6 before, because c is 5 microfarad, right? Integral from so let's get what I of t will be. I of t is what? 20 milliamperes. So that's what we use. From 0 to 2, 20 milliamperes, so it's 20 times 10 to the power minus 3 dt, plus t naught is 0, so that's v of 0. So what do we have? It means that this is 0, right? So when we integrate this, we have 20 times 10 to the power minus 3. This should be times 10 to the power minus 6 of t into bracket t, right, over 5 times 10 raised to the power minus 6. That is, this is from 0 to 2. So what do that give us? That will give us 4000 t. That is v of t equals to 4000 t. And of course, we know that it is from 0 to 2. So which means that for the second equation, v of t is equals to 4000 t for 0 less than t less than or equals to 2 milliseconds. So this for the second case, right? So for the third case, what do we have? This is the third case. I of t is also 0, right? So if you should write that, that is, we have 0, v is equals to 0 when t is less than or equals to 0, is equals to 4000 t when 0 is less than or equals to t less than or equals to 2 milliseconds, and of course is equals to 8 when t is greater than or equals to 2 milliseconds. And this is the answer. You can see that it's very, very simple to understand. So let's now go to the energy storage for capacitor. That is how capacitor stores energy. So to determine the energy stored in the capacitor, we begin with the power delivered to it. P is what? It's equals to voltage times current, right? So what is current? Current is C dV dt, right? We have V multiplied by C dV dt. So what does that give us? It means that the power is equals to CV dV dt. The change in energy stored in its electric field is simply what? The integral of P dt. That is, when we cross multiply, we have P dt, and remember that energy is power times time, right? So that's, which means that when we integrate power with respect to time, we get energy CV dV. So when we integrate from T naught to T, and this of course from T naught to T, so what do we have? This gives us P, so this gives us CV squared over 2, right? We are integrating with respect to V, right? V of T naught, V of T, right? So these are the boundaries. CV squared over 2, because when we integrate V, C will be a constant because we are integrating with respect to V. So therefore we have V squared over 2. So which is still equals to CV squared over 2, and the boundary is V of T naught. If you open the boundary, what do we have? It means that the energy is what? 1 over 2C into bracket V of T squared minus V of T naught squared. Basically, if we select a zero energy reference at T naught, implying that the capacitor voltage is also 0, and at that instance, what do we have? This will be equals to 0, and therefore we have the energy to be equals to 1 over 2 CV of T squared, or basically we say energy is equals to 1 over 2 CV squared. So the energy stored in a capacitor is 1 over 2 CV squared. So let's solve an example with this. The question says that we should find the maximum energy stored in the capacitor and the energy dissipated in the resistor over the interval 0 to 0.5 seconds. So basically you can see that the energy stored in the capacitor varies with time, and we are asked for the maximum value over a specific time interval, and we also asked to find the total amount of energy dissipated by the resistor over this interval. These are actually two completely different questions. The only source of energy in this circuit is the independent voltage source, which has a value of what? 100 sine 2 pi t volt. 2 pi t volt. And we are only interested in the time interval of 0 to 0.5 seconds. So let us determine the energy in the capacitor by evaluating the voltage. So energy is what? 1 over 2 CV squared. So what does that give us? The capacitor is 20 microfarad. This is 1 over 2 multiplied by 20 times 10 raised to the power minus 6 multiplied by 100 sine 2 pi t sine 2 pi t squared. Right, so if we solve this, we should have 0.1 sine squared 2 pi t, and the unit is joules. That's very, very simple. Therefore, we can get the current going through the resistor IR. How do you get that? You can see that the voltage source is parallel to each of these passive elements, and if the voltage source is parallel to components like that, they will take the same voltage. So therefore, IR is V over R, right, by Ohm's law, and V is what? 100 sine 2 pi t over 1 times 10 raised to the power 6. Right, so this will give me what? 10 raised to the power minus 4 sine 2 pi t amperes. So how do I get the power? Right, the power is I squared R. Don't forget, P is equals to IV, and therefore P is equals to IV, and by Ohm's law V is IR, so multiply by IR, and therefore is equals to I squared R. So let's do that. So the PR is equals to I squared R, right? And therefore you get what? 10 raised to the power minus 4 sine 2 pi t squared multiplied by our R is 10 raised to the power 6, that is 1 mega ohm. So which is equals to what? This will give me 10 raised to the power minus 8 multiplied by 10 raised to the power 6 sine squared 2 pi t, which is equals to 10 raised to the power minus 2 sine squared 2 pi t. So energy is what? Integral of P dt from 0 what to 0.5. They said we should get it for an interval between 0 and 0.5 seconds. So what do we have? That's from 0 to 0.5, 10 raised to the power minus 2 sine squared 2 pi t dt. So you can choose to integrate this, that is, you have to convert this using trigonometric identities and you solve for it. I give this to you as a challenge. Solve this. So that is very, very simple to calculate. The energy in a capacitor, stored in a capacitor, right? Then the power that is dissipated through the resistor. Power is usually lost through the resistor, it's usually dissipated through the resistor, while the capacitor stores energy. That's very, very simple. As a summary again, let me tell you the important characteristics of an ideal capacitor. Number 1, for an ideal capacitor, there is no current through the capacitor if the voltage across it is not changing with time. If the voltage is constant, there is no current through it. So basically, I is equals to what? We said I is equals to C dV dt. If the voltage is constant, what do we have? C d dt, a constant. Let me say it as K because we already have C here. And when we differentiate the constant, what do we have? We have 0, which means that I will be equals to 0. So therefore, there is no current through a capacitor if the voltage across it is not changing with time. A capacitor is therefore an open circuit to DC. That is, when we have a DC source. Let's, for example, you have a DC voltage source, and therefore the voltage passing through the capacitor is DC. Therefore, the current will be 0. And when current is 0, we call it an open circuit. Therefore, a capacitor is an open circuit to DC, to direct current. The second important characteristic is that a finite amount of energy can be stored in a capacitor even if the current through the capacitor is 0, such as when the voltage across it is constant. Yes, there's still a finite amount of energy that can be stored in the capacitor even if the current through the capacitor is 0. And the third one is that it is impossible to change the voltage across a capacitor by a finite amount in 0 time, as this requires an infinite current through the capacitor. What does that mean? It means that a capacitor resists an abrupt change in the voltage across it in a manner analogous to the way a spring will resist an abrupt change in its displacement. This is very, very, very easy to understand. A capacitor will resist an abrupt change in its voltage. That is, at a particular point. At a particular point, let's say T is equals to 0, right? So the current before T gets to 0 and the current before T, when T passes 0 will be equal. It resists an abrupt change in it. So in the calculus, we will say that the limit tends to 0. That is, when the limit as T tends to 0, whether it is coming from the right or coming from the left, for the voltage on the capacitor, right, it is usually equals, it usually exists. So in engineering calculus, when you say when the limit as is tending to 0 from the left is not equals to when it's tending to 0 from the right, it means that the limit does not exist. So what this means is that the limit exists. So there's no, it resists an abrupt change. That is, when it is coming from the left, The capacitor resists an abrupt change in voltage. That is, when it gets to zero and it's already leaving zero, it's still taking that particular amount. It resists itself to change its voltage. I hope you understand. Then the fourth and the last one is a capacitor never dissipates energy. It only stores it. It is only a resistor that dissipates energy. Same thing as inductor, as we will learn soon in our next tutorial. A capacitor never dissipates energy. It only stores it. Although this is true for the mathematical model, but it's not true for a physical model, of course, because due to we have finite resistances associated with the dielectric as well as the packaging. I used to say this to my students, that most of the things we do in physics, the formulas we get, they only apply in ideal cases. They don't apply practically. Most of them, and not all of them. So with these few points and with this elaborate explanation, I'm very sure that you understand capacitors, how they store energy, the voltage and the current relationships in a capacitor. See you in the next tutorial for inductors. Thank you.